So here we're going to calculate the lattice energy using the Born-Mayer equation for lithium fluoride. So here we have the Born-Mayer equation, and to get started, we're going to start here with Avogadro's number, 6.022 times 10 to the 23rd per mole. This is here to make sure our answer comes out in joules per mole. The next factor is the Madelung constant, which depends on the lattice type. So lithium fluoride crystallizes in the same structure as sodium chloride. So we'll use the value of the Madelung constant for that lattice type, 1.74756. And that's unitless. Okay, then we're going to multiply by the charges of the ions. So here in this case, we're going to have a +1 charge for the lithium ions and a -1 charge for the fluoride ions. Now we're going to divide that whole thing by the distance between the two ions. So we know that the ionic radius for lithium is 76 picometers and the ionic radius for fluoride is 133 picometers. And these are things that we look up. They're available in tables. And so if we add those together, we get that the radius is 209 picometers. Now a picometer is 10 to the -12 meters. And so I'm going to go ahead and convert that to meters because we'll see in the next step that our units need to be in meters. Now we're going to multiply all that by this e squared divided by 4 pi epsilon term, which relates to the charge on an electron and also the permittivity of a vacuum, so the ability of an electron to sort of get through free space. And so those are just some constants, and if we put them together, we get that their value is 2.307 times 10 to the -28 joules times meters. And so that's why our distance needs to be in meters. And then finally, we're going to multiply that, sorry, I kind of ran out of space here, multiply that by this 1 minus rho over r naught term. So 1 is easy enough. Now rho is a constant that depends on how compressible a crystal is. And so that's kind of a fuzzy term for you. This is something that Born and Mayer kind of worked out empirically, but you don't really need to know what that is. You're going to use 30 picometers. That's a pretty reasonable number, especially for alkyl halides, but for our purposes, close enough for other lattices too. So that's 30 picometers, so this is just the Born repulsion constant. And then we're going to divide by the r naught, the distance between the ions, and here we're going to leave it in picometers because rho's in picometers. Okay, so when we put all of those things together and we put it into our calculator, I get -991,505, and our units are joules per mole. Okay, now I'm going to convert that to kilojoules. Okay, remembering that there are, for every 1 kilojoules, that's 10 to the 3rd joules. All right, and so that comes out as -992 kilojoules per mole. Okay, so what does that number mean? So we found with the Born-Haber cycle that the enthalpy of the lattice enthalpy was equal to -1050 kilojoules per mole. Now, those aren't exactly the same number, but if we calculate the discrepancy as a percentage, so we get -50 minus -992 divided by -1050 times 100%, we see that the discrepancy, the sort of percent error, if you will, is only 5.5%. This is really pretty good agreement between the theory and the experiment. And so what that tells us is that the bonding in lithium fluoride is mostly ionic because it is pretty well represented by this electrostatic model for bonding. And so that makes sense with what we know about lithium fluoride, that these are small, hard ions that are mostly involved in ionic bonding. We also notice that the experimental lattice enthalpy, the -1050 kilojoules per mole, is slightly higher magnitude. So this is even more stable than the Born-Mayer equation predicts. So that direction is important. That extra stability is the influence of covalent bonding between between lithium and fluoride.